you could actually see what kind of discount rate they're using before you make your decision.
No, I just gotta win.
Yeah. Yeah, well, you could also, you know, Ian, it's just whenever you buy a lottery ticket, it's unfair, very unfair game. Because there's several reasons for that. One is about half of the revenue they collect goes to the state, and the other half goes to pay out the winners. So right there is a big chunk. So it's not a fair game.
Yeah, but when I buy that ticket for the next 3-4 hours,
Okay, no, that's a good point. That's a good point. We are getting a little bit off subject, but no, that is a good point. Even though it's not a fair game, you imagine, if you bought a ticket, you imagine, well, I could win this. And maybe the prize is, I don't know, $20 million. Powerball, I think we started with $20 million. Imagine if you won $20 million.
Take everyone.
Wow, yeah, that's right.
Probably drop out too.
And so then you get a certain pleasure out of thinking about that. So maybe that's worth it. Even though the chances of you winning, it's more likely you'd be struck by lightning, killed. But nevertheless, you got the pleasant experience thinking about what you would do if you had $20 million. Okay, the last problem is this. Part C. In this one, the question is the amount of time it takes for a sum of money to triple in value if a continuously compounded interest rate is 3%. So the way to do this one, let me move C over here. See, you start off with A, but you want the future value to be 3A. So set V equal to 3A. So we get 3A equals A times E, and our R here is 3%. 0.03 T. Now in this case, T is not specified. T is something you want to solve for. So you basically solve this equation right here. Now notice it doesn't matter what A is. A could be 1,000, it could be 2,000. It doesn't matter, just divide both sides by A. And this equation reduces to this. 3 equals E to the 0.03T. Now that you understand logarithms, you could solve for this. Just take the logs of both sides. You get the natural log of 3 equals the natural log of E to the 0.03T. And let's just leave this as the natural log of 3 for now. You can bring this 0.03T down using our rule number 1, logarithms, times the natural log of E. And the natural log of E is what? 1. E to the 1 power equals E, so that's 1. So this is just 1. So the answer is just T equals the natural log of 3 divided by 0.03. And actually, you could answer this question more generally. How long do you have to wait for the value of your money to triple? It would be the log of 3 divided by whatever the interest rate is. Here we're assuming the interest rate is 0.3. But if you use some other interest rate, you just divide it. And doing this calculation, what I got was 36.62 years. Rounded off to 2 decimal places. You've got to wait a long time for your portfolio or a certain sum of money, A, to triple in value. if the interest rate is only 3%. If the interest rate's higher, you can put your money in the stock market and get 9% per year, then you wouldn't have to wait so long. But if you're only getting 3% a year, it takes a long time for the value of your money to triple. Okay. Any questions, comments, or? We were discussing the wine problem yesterday, how long you should let wine age. And just to quickly review that problem, let's go back and look at it again. We assumed that the value of the wine, the future value of the wine, was just given by this equation. Some constant K times e raised to the t to the 0.5 pi, or the square root of t. That's the future value of wine. What we want to do is store the wine until the present value of the wine is maximized. You don't want to maximize the future value, because money received in the future is not worth as much as money received today. You want to maximize the present value. The present value is just this. A equals the future value times e to the minus RT. So you got to discount that future sum of money by e to the minus RT to convert it into a present value. This is what you want to maximize. And we did this yesterday. We did this yesterday and worked it out. And for R equals 0.1, we showed that the optimal value of t was 25 years by looking at the first order, second order conditions. There's a more intuitive way of thinking about this problem. The more intuitive way of thinking about this problem is as follows. What you want to do for any asset you own that's appreciating over time, you want to continue to hold that asset until the growth rate in the value of that asset is just equal to the market interest rate. And the market interest rate, let's say, is R. Okay. Now, what is the growth rate of V? What is we'll call it R sub V. What is the growth rate of V? We just emphasized R sub V is the growth rate. And we're using a continuous time model, so it's continuous growth rate. What is the formula to calculate the growth rate of V? What is R sub V? Kelsey, I can see that you want to answer.
Maybe. Is that the 1 over V divided by 3?
Okay. Oh, only in this case, it's V rather than Y. So it would be, taking that into account, Kelsey, the formula would be
1 over V dV dt?
1 over V times dV dt. See, dV over V is just the proportional change in V per unit change in time. So it's a growth rate. It's a proportional or percentage change in V per unit change in time. Okay. And let's calculate dV dt. What is dV dt? remember that rule we went over? We went over the rule in terms of y. But now we're just changing y to v. So what would dv dt be here? The first derivative of v with respect to t.
0.5.
Right?
So negative
Right.
0.5
Right.
K E0 T0 0.5.
Exactly. What you have here, this exponent, think of that as being f of t. So you want f prime of t times that expression, k times e to that. So you take the derivative of the exponent, as Brianna said, so it's 0.5 times t to the minus 0.5 times k times e t to the 0.5. That's dv dt. To get the growth rate, what we have to do is multiply by 1 over v. And if I multiply by 1 over v here, I have to do the same thing, or just divide by v. And what is v? Well, v is given to you, it's just this. So you see what happens? This cancels with that, and the growth rate is just this, 0.5 times t to the minus 0.5. So it's a simple expression. Or you could rewrite this as just this. The growth rate of v, let me put r sub v here. R sub v reduces to just 0.5 divided by the square root of t. So you can see what happens to this growth rate. As time goes on, this denominator gets bigger. So this growth rate is getting slower and slower and slower. So what you want to do is continue to let this wine age until it's the growth rate of the value, the appreciation rate of wine is just equal to the market interest rate. So if we assume the market interest rate is 0.1, you want to solve this equation. And solving that equation, we get multiply both sides by the square root of t. We get 0.5 equals 0.1 times the square root of t. Divide both sides by 0.1. 0.5 over 0.1 is 5. 5 equals the square root of t. T square both sides, you get t equals 25, which is the same answer we got before. Only this is, I think, a little more intuitive. This is definitely more intuitive. So anytime you have an asset that's appreciating in value over time, the optimal time to sell this asset is when it's appreciating at a rate just equal to whatever the market interest rate is. In this case, we assume that little r was 1. And we can actually draw a nice picture to illustrate this. I urge you, whenever you can draw a graph to illustrate something, do so. It'll help you understand it better. Time on the horizontal axis, the growth rate of v, the growth rate of v on the vertical axis. R sub v, given by this formula right here. So if you graph this function, it's going to look like this. Notice, as t goes to infinity, the growth rate is approaching 0. Never quite reaches it. Yes, Todd?
Why is R sub v dv over, or why is it not dv over v over dt over t? Why is it 1 instead of t there? I guess I don't understand why it's not the...
All right, let's go back. By definition, the growth rate of v. Now it's understood that v is some function of time. So the growth rate of V is 1 over V times dV dt. Or I could rewrite this, Tyler. I want to bring this V up here, so it's dV over V dt. So in words, this is the proportional change in V. This is the change in V divided by V. So this is the proportional or percentage change in V per unit change in time.
Okay, I don't understand why there's no proportional change in T, why it's just DT unbounded.
Okay, because it's a percentage change in V per year, it's not an elasticity. It's not the percentage change in V over the percentage change in time. It's the percentage change in V
Yeah,
per year.
okay.
So suppose,
Yeah, so it depends on what T is
Yeah.
measured in, right? Is kind of what we're thinking of. Is it in percentage
Well,
changes or is it in
no,
unit changes?
it's not in percentage changes.
Well, no, I know,
Yes.
but I'm saying
Yeah.
that's
Right.
kind of the difference.
Exactly.
Okay.
If this were an elasticity of V with respect to T, then it would be dV over V divided by dt over T. So then it would be the percentage change in time.
Okay, that makes sense.
But, for example, take something like GDP. GDP grows, say real GDP grows at, say, on average 3% a year. So it's 3%, it increases by 3% per year. So it's not, you don't want the percentage change in time, you just want the change in time.
Mhm. Okay.
Yeah. But it's kind of close to the idea of elasticity. The elasticity of V with respect to T would be this. It would be the percentage change in V per percentage change in time. But that concept, we don't find that very useful. So it's almost elasticity, except you're just dividing by dt. Good question. Okay, so here is our growth rate of V. Notice as the t goes to infinity, the growth rate in the value of this line approaches 0. And also, very importantly, what is the limit of the growth rate as t goes to 0? From the right-hand side, of course. As this t is getting smaller and smaller and smaller, closer to 0, what happens to the growth rate? Yeah, yeah. It approaches this infinity, yes. So it's going like this. It never quite reaches this vertical axis, but this growth rate. And this is, you know, this is, I noticed this with trees. This is not quite true, but you know when you plant a new tree, like the first year, it'll double or triple in size. It's growing very rapidly at first. But then, you know, after the tree is 20 years old, the growth rate really slows dramatically. So that's what we're assuming. In this particular case, the growth rate is assumed to decline like this. So when you want to, in this case, we're talking about wine. When do you want to stop aging the wine? When it's appreciating at whatever the market interest rate is. And let's assume that the market interest rate is 10%. Maybe you're in debt, you have a credit card debt. And so the more money you get, the more of that credit card debt you can pay off, 10%. So that's would be a rate of return. Okay, so it's kind of high. All right, but in any case, what would this be? 25. When the wine is less than 20, this must really be a good Bordeaux wine if it appreciates like this. You would age it for 25 years. It has to be really first class. So if you let it age for less than 25 years, it's still appreciating in value more than 10%. So when it's just appreciating by 10%, that's when you sell it. Because if you hold on to the wine, it continues to appreciate, but it is appreciating at a rate less than the market interest rate. If that's kind of an more intuitive solution to this problem. The fact that the growth rate is declining over time, that guarantees that the second order condition is going to be satisfied and that you'll get a maximum when you sell the wine when the RV equals 0.1. Sometimes these problems are phrased not in terms of wine, but for example in terms of timber. If you have a stand of timber, the longer you let the trees grow, the bigger they get, the more lumber you get. So you might want to let the trees continue to grow as long as they're appreciating at a rate that exceeds the market interest rate. So that's another type of problem you can do. Very similar to the water problem the book discusses. Now we are ignoring some things. If you have a stand of timber, you may have to water the trees every now and then or safeguard the trees to make sure nobody steals them. So there might be some annual costs that you would have to add in to the problem. But ignoring those annual costs, you would let the trees grow until their growth rate is just equal to the market interest rate. And that would maximize the present value of the trees. So lumber companies are surely interested in these sorts of problems. They would have, if you were working for a lumber company, they would have probably a better idea of what this V function really is. It wouldn't necessarily be this function, it might be something else, it would be something similar. And it is certainly true that the future value of trees is going to have a growth rate that diminishes over time. That's important. All right, let's move on to some new material. Let's begin our discussion of optimization problems with the two or more choice variables. Let's start with a case where z is a function of x and y. So x and y are your independent variables, z is your dependent variable. And let's assume you either want to maximize or minimize the value of z, the value of your function. X and y then are your choice variables. So you want to choose the values of x and y so as to get the maximum value of z. Now, I'll just straight away give you the first order and second order sufficient conditions, and then we'll discuss where they come from.